morning, boys. In our last class, we have discussed about hydrolysis of salt. You have seen that reaction of salt with water, making the solution acidic or basic. This is known as hydrolysis. Today, our next topic is solubility product, denoted by KSP. Before going to this topic, you consider HCl. It is a salt, sparingly soluble salt. Sparingly soluble salt means those salts which are assumed to be almost insoluble in water, such as calcium carbonate, CaCO3. Apparently, it is such a salt that we say insoluble in water. These salts are also very slightly soluble in water. For those type of salts, they are known as sparingly soluble salts. There is an equilibrium system attained. The equilibrium system attained between the solid salt and the ions present in the solution. This equilibrium is attained only in case of sparingly soluble salts. There are many examples you will come to know. Silver chloride, phosphate, all phosphates are insoluble except sodium, potassium, ammonium. All sulfides are insoluble except sodium, potassium, ammonium. There are a series of family of insoluble salts, and truly speaking, they are sparingly soluble salts. Now see, for this equilibrium system, there is an equilibrium constant, and the equilibrium constant K is denoted by concentration of silver plus into concentration of Cl minus molar concentration by concentration of silver chloride, AgCl. As you know that AgCl is solid, therefore its concentration will not change. It is considered to be a constant. Therefore, this constant multiplied by this constant is denoted by Ksp. This constant multiplied by this constant value denoted by Ksp. Therefore, Ksp for silver chloride is concentration of silver ion into concentration of Cl minus ion. Now, this is the expression of Ks, equilibrium constant. Equilibrium constant denoted by Ksp is known as solubility product. This equilibrium constant is known as solubility product. Now, supposing the silver chloride, the solubility of silver chloride is S. If you consider solubility of silver chloride of HCl at room temperature, if you consider, is as mole per liter. So it is very slightly soluble. Solubility is less than 0.01 molarity. So you consider the solubility of silver chloride in water is 0.01 mole, as mole per liter. So at equilibrium, as mole per liter will dissolve in water. Therefore, the concentration of silver ions will be as, and concentration of Cl minus ion will also be as mole per liter. So this is the concentration of silver ion at equilibrium, and this is the concentration of chloride ion at equilibrium. Therefore, in terms of solubility, Ksp for silver chloride can be denoted as Ksp for silver chloride can be denoted as into as that is equal to S square. Now, the solubility product and solubility of the given salt, this relation is very important relation between Ksp and S. This relation is very important relation, and the relation varies from the type of salt to another type of salt. Say salt of type AB, this is one that I want to have. The relation of Ksp and S will be Ksp equal to S square. But if you change the type of salt, for example, we are taking another salt, barium phosphate, Ba3PO4 barium phosphate. It's a solid, aqueous, 3 2 plus recently dissociation. Barium phosphate dissociates in water to form 3 barium ion and 2 phosphate ion. Now consider its solubility. Solubility of barium phosphate in water is as mole per liter. Therefore, add equilibrium, and equilibrium, the concentration of barium ion will be 3s, concentration of phosphate ion will be 2s, molarity. Therefore, the KSP, expression of KSP for barium phosphate will be barium ion, concentration of barium ion to the power 3, concentration of phosphate ion to the power 2 to the power 2. Therefore, KSP in terms of solubility, KSP barium concentration is 3s, so 3s power 3 into 2s power 2. So this is equal to 3 into 3 into 3, 2 into 2. That means 27 into 4, 27 into 4 s to the power 5. So this is equal to 108 s to the power 5. So see, this is the relation between KSP and S for a salt of barium, a salt of dye A3B2, a salt of dye A3B2. The relation in A3B2 means 3 cation and 2 anion, A3B2, and this is a salt of AB type, AB type. So all salts of AB type will have this relation, KSP equal to S square. All salts of A3B2 type, the relation between KSP and S will be KSP equal to 108 s to the power 5. Remember, this type of salt and this type of salt will have the same relation, A3B2 or A2B3. If you interchange their subscript, it will not matter. A3B2 or A2B3, both types of salts will have the same relation between KSP and S. Clear? Now see, similarly, if you go from a B2 type of salt to A2B type of salt, the relation between KSP and S will be same. And you can find out what is the relation between KSP and S for a salt of type B2 or A2B, that you can find out by your own. The relation, the process of finding the relation is like this. You have to write the dissociation correctly. Then considering the solubility of the salt as S, you have to write the concentration of the cation and concentration of the anion, write the expression of KSP, putting the values of concentrations or add equilibrium, you will finally get the relation between KSP and S. So solubility, product and solubility, this relation is very important. If you are given the value of KSP, you can find out the solubility of the salt at room temperature in water. If you are given solubility of the salt, you can also find out KSP. So remember, KSP is the equilibrium constant. Equilibrium constant for the solubility of a sparingly soluble salt, because those salts which are very soluble, like NaCl, those salts which are what we say slightly soluble, they do not attain equilibrium. Most of the salt will be dissociated, they do not attain equilibrium. Only equilibrium is attained by the insoluble salt, which in our language we are telling sparingly soluble salts. Equilibrium is attained, equilibrium is possible only for insoluble salts, or in scientific term they are known as sparingly soluble salts. Now let us see an example with the help of a problem. See, I am writing the problem here. See, what is given? KSP of cuprous sulfide at 25 degrees centigrade is given. KSP is always given in water, remember. KSP. It is always measured in water medium, aqueous medium. Find the solubility of cuprous sulfide in water at that temperature. Now see, cuprous sulfide Cu2S dissociates as Cu plus and S2 minus. So this is the dissociation of cuprous sulfide. Its solubility, consider the solubility as mole per liter. Therefore, at equilibrium, its concentration will be 2S, its concentration will be S. Therefore, KSP equal to concentration of Cu plus to the power 2 into concentration of sulfide ion. This is equal to 2S to the power 2 into S, which is equal to 4S cube. So what is the relation? The KSP equal to 4S cube. For a salt of type Cu2S means A2B type, A2B, 2 cation, 1 anion. Now this is given, KSP is given, therefore you can write that 4S cube equals to KSP, KSP means 4 into 10 to the power minus 12, 4 cancel, S cube equals to 10 to the power minus 12, therefore S equal to 1 into 10 to the power 1 into 10 to the power minus 4 mole per liter. See, the solubility of cuprous sulfide in water is 1 into 10 to the power minus 4 mole per liter. That means 0. This is equal to 0.0001 mole per liter. So just imagine that its solubility is very less. Only in 1 liter water 0.0001 mole will dissolve in water. So almost it is insoluble. You cannot understand it externally. If you put cuprous sulfide in water, it will apparently you will see that it is insoluble as it is. After adding water to it, you will find no change, very slight change, and this is because of such solubility. Clear? Now the solubility of the sparingly soluble salts gets changed in presence of a strong electrolyte, what is common ion effect, that we have already discussed. Let us see an example of common ion effect. See, solubility of cuprous sulfide is given. Solubility of cuprous sulfide at 25 degrees centigrade is given. Find the solubility of cuprous sulfide in, I am just in 0.1 molar NH4 as at that temperature. 0.1 molar NH4 as for ammonium sulfide, NH4 whole 2 as in ammonium sulfide at that temperature. So see, ammonium sulfide is fully soluble. That means the entire ammonium sulfide will dissolve in water. So in the solution there is 0.01 molar ammonium sulfide. Now see, Cu2S dissociates as Cu plus S2 minus. Clear? Ammonium sulfide dissociates as NH4 as dissociates as 2NH4 plus S2 minus. So see this one, this ion is common. So there will be common ion. Supposing the solubility of Cu2S in ammonium sulfide is X mole per liter. You consider S mole per liter. X, change it. Because when you write S, that means solubility in water. We are writing the solubility of cuprous sulfide in ammonium sulfide solution in X mole per liter. Now X mole per liter, because its solubility will be decreased due to common ion. You have just seen the solubility in water, it was S equal to 1 into How? Say it is X. Concentration of CO2 ion 2X, because X is the solubility of cuprous sulfide in ammonium sulfide solution, and concentration of sulfide ion will be X. Again, from ammonium sulfide, this is 0.1 molar solution. So entire ammonium sulfide will dissolve in water to form 0.2 molar ammonium ion and 0.1 molar sulfide ion. Clear? 0.1 molar sulfide ion. Now see, the sulfide ion concentration is X plus 0.0. Remember, sulfide ion concentration is X plus 0.01. X is coming from the dissociation of cuprous sulfide, and 0.01 molarity is coming from the dissociation of ammonium sulfide. Therefore, when you write Kc, expression of Kc, this is equal to concentration of Cu plus ion to the power 2 into concentration of sulfide ion. Now see, it is given Kc is constant term, it will not change. 4 into 10 to the power minus 12, this is equal to X, 2X to the power 2 into S is X plus 0.01. So see, we have written the concentration of sulfide ion X plus 0.1. Now you have to solve it. Remember, X is very smaller than 0.1. X is the solubility of cuprous sulfide. You have seen the solubility of cuprous sulfide 0.0001 in water, and in ammonium sulfide solution it will go decrease, it will further decrease. Therefore, X will be very less than 0.1. Therefore, you can neglect X from here. Neglecting X from here, it will be 4 into 10 to the power minus 12 equals to 4x cube into 0.1. So 4 cancel. Therefore, x cube equals to 10 to the power minus 11. 10 to the power minus 12 into 10 to the power minus 11. So x cube equals to 10 into 10 to the power minus 12. I am writing it this way so that you can find out the cube root of 10. X equal to cube root of 10 into 10 to the power minus 4. Cube root of 10 into 10 to the power minus 4. Sorry, it is 4x square. I am wrong here. It is 4x square. So 4 and 4 cancel. 4x square power 2 into 10 into 10 to the power minus 11. So it is x square equals to this. So x equal to square root of 10 into 10 to the power minus 6. See. So the value of x, square root of 10 into 10 to the power minus 6. So it is 3 point something into something into 10 to the power minus 6 mole per liter. So see the value. In water, the solubility of cuprous sulfide is 1 into 10 to the power minus 4. In ammonium 0.1 molar ammonium sulfide solution, the solubility of cuprous sulfide is 3 into 10 to the power minus 6. How much it is decreased? 3 into 10 to the power minus 6. So in water it is 0.0001 molarity, and it is 0.000003 molarity. So notice the decrease. Decrease is 0. Notice the decrease from 0.001 molarity to 0.000003 molarity. So this is common ion. So these problems you have to handle. You have many such examples in your book. You will solve some problems of solubility product and solubility so that you can build up a clear concept there. Okay boys, thank you. So today our class is over. Next class we shall discuss about the buffer solution. Thank you boys.